All right, good afternoon. Thank you for joining our RC design class again. And today is Thursday, as I was just discussing with some of your friends that we may have plans for the next week. But I still want to warn you that our second exam is coming right after the spring break. All right, so if I were you, I will plan out at least 2 or 3 days, maybe 2 days minimum, just to go over some of the materials we have covered so far for the exam number two. Okay, and we will have a review session right afterwards. I believe it's Monday that week, and we'll go over some of the basic materials. But I can safely tell that there are going to be three problems. The first problem going to be a lot of filling the void and filling the blank and multiple choices. And we see a lot of sheer design concept there for the first problem. Okay. And for the second and the third problem, we might have um, one irregular section flexure and one shear or two shear problems. Okay. Uh, when I say we might have irregular section and shear, that means that I have the section designed out and it's going to be a hollow section. That means a section with an opening or duct in the middle of it. But whether it's going to be a irregular section flexure or just a good old fashioned shear design, I yet to decide. Okay. I made two versions of it. So you might see one version or the other. All right. So that's about the exam. Like I said, I'll go over some more specifics on Monday, and I'll show you some of the past exams on Monday as well. So make sure you make back on time, all right, after spring break, so we can do the review together, all right? Okay, I think I have most people here, so I'm just gonna go back on the lecture. But before I start, let me make a pause. And any questions so far on the course or on the homework, on the exam, anything, folks? Anything? All right. Okay. Well, email me if you have any questions, and be safe during the spring break, and don't break any ankles, and make yourself back on time. All right. Okay. So let's get back to it. Okay. Let me share screen, and we were talking about the one-way slab last time, and we made some examples. And let me just get this thing started. And we left at a design problem, right? And specifically in the middle of it, we talk about how we're going to do the calculations for it, okay? Let me see. Homework ready before. Yes, so sorry, Henry. I have finished them all yesterday, but haven't gotten time to transfer that. What happened is that I had internet problem again Monday, so I download your homework 4 and 5. So I print them out and graded number 4, finished number 4 yesterday and got into number 5, almost done with number 5. So I have to transfer some of the write-up I have on your canvas. But yes, would definitely be graded before exam, actually this weekend. Sorry for the delayed again, okay? And then quickly get back on one-way slab. So this is where we left at last time, right? So quick review, if we forgot, we start with a simply supported condition, all right? Now, this is a very important part, simply supported, because we need to calculate the moment based on that. All right, and now the applied loading on the simply supported beam have two parts. One is dead load and the other is live load. And the dead load is including the self weight only. That means you have to calculate the dead load for it. All right, and the live load is 150 pound per square foot with the concrete property of 4 KSI, yield strength of 40 KSI. And just want you to notify or notice that this is a little bit low on the low side of it. Okay, so you have to make some adjustment based on this. All right. Okay. Now this is the first important equations, and you don't have to remember it, but just know you got to apply this if you're not given HF during the second exam. All right. So this is the equation for it. You have to satisfy this equation, and again, L1 is the span length direction along the bending span, and you have to make sure that you provide a height that is bigger or equal to than bigger than or equal to this number. So we select 5 inches. All right. And then again, for this case, we need to provide a clear cover. And for one-way slab, usually it's interior. That means it's not exposed to extreme weather conditions. So we usually apply a very thin concrete cover of 3/4 here, and that is clear from edge to edge, showing in this figure here. So we can estimate the depths, right? Estimate the depths based on it, right? And again, for the bars, we always assume there's going to be 1 bar per foot, 1 bar per foot. All right. And the bar we use for one-way slabs either number 3 or number 4. In this case, we use number 4. So you already know the size of the bar and bringing to that gets you the depths. All right. Now, on the other hand side, if you don't know anything about the cross section, you have to make assumption that you can always use D equal to 0.95 of HF. All right. But this is just assumption. I still prefer this one. I prefer this one in most cases. All right. Okay. So after first step, we said, okay, the height is going to be 5 inch, the depth is going to be 4 inch, and it's going to be number 4 bars. All right, so that's what we end up with. And starting from there, we need to find out what is the required reinforcement per foot, okay, per foot. This is very, very important, all right? So anything you do with one-way slab, matter of fact, for all the slab design, is always something per foot, has to be per foot. Okay, so we're given this section, we need to try to find the dead load. So that is by using the area and multiply the density of the concrete. All right, and this is per foot again, so end up with some number here, but again, this is per foot square because you have the area. All right, and then you plug this number back into the applied loading, 1.2 dead plus 1.6 live, you got 315 pound per square foot, and that is the distributed load you have. To get a moment, right, we use this equation, which is omega u L1 squared divided by 8. This only apply with simply supporting condition, the uniform distributed load. All right, so that gave us 3.94 kip foot per foot. Again, per foot. All right, 3.94 kip foot per foot. Okay, so that is the moment this slab is seeing in this one-way slab direction. All right, so now we have the applied moment. The name of the game is to find the corresponding reinforcement for it, right? So you learned that from the flexure design, AS per foot equal to MU divided by phi Fy D minus half A. D minus
Hey,
half A.
Professor, I don't mean to interrupt, but I got a friend of mine who's in the waiting room.
Oh, sorry, let me see who's there.
Austin.
Oh yeah, sorry about that, okay. Yeah, thank you for reminding me, all right? So now we need to find the distance, which is between the compression, and tension. And this D minus half A here roughly can be estimated as 0.95 D depth again. All right, 0.95 D depth again. All right, so that is how we find the distance. So this is where we left at, right? Now just bring the number into this equation, AS per foot, that is equal to, bring the number in, 3.94 kip foot per foot. Okay, that is the bending moment, right? And divided by phi, assume phi equal to 0.9, so 0.9 multiplied by 40 ksi, that's the yield strength of the bar, and multiply by this number here, d minus half a, and we say we don't know that, so 95% of the depth, which is 4 inches. All right, so that gives us a number of, right here, a 0.346. And after you consolidated the unit is 0.346 inch square per foot. 1 second, I got another weight room here. 0.346 inch square per foot. All right, so that is so-called required. Okay, so this is required reinforcement needed for the one-way slab per foot, per foot. But this is not enough, right? We said, okay, this is required, okay? But we now, given this number, can confirm the actual compressive zone A now, right? How do we do that? So A should equal to AS Fy divided by 0.85 F prime C B, where B equal to 12 inch or 1 foot. Okay, so that is the width of the section, right? Unit strip again. So this equal to a 0.346 inch squared per foot, all right? Multiplied by 4t KSI, 40 KSI divided by 0.85 and 4 KSI here and multiplied by 12 inch. Okay, and again, this one is unit strip here, unit strip here. Okay, don't forget. So once everything's said and done, I have an effective compressive zone of 0.339 inch. Okay, 0.339 inch. All right, so once I have my effective compressive zone, what I would do is I get my effective compressive zone. I need to confirm or recalculate A again, recalculate A as per foot again. So have to iterate, right? So AS per foot has to be then greater than or equal to mu divided by phi, mu divided by phi Fy, and D minus half A. And lucky for us, we already have A. And so this one, the 3.94 kip foot per foot, all right? And I want everything back to inches. So I multiply conversion of 12 inch per foot, all right? I want everything convert back to inches. So multiply the conversion and then 0.9 here, and this is 40 KSI, okay? And this is 4 inch minus 0.339 inch divided by 2. All right, divided by 2. Don't forget that 2 right there. All right, so now AS per foot, AS per foot has to be greater than or equal to 0.343 inch squared per foot, inch squared per foot. Okay, so this, ladies and gentlemen, is my final number for the area reinforcement selected for the slab, for the slab. All right, but let me say something here, okay? So AS per foot here, this is what? Converted reinforcement, converted reinforcement, okay? So I need to find a bar that is AB, remember? This is the area of the single bar, remember? AB, okay? And I want to convert that, this is 12 inch, because it's unit length, unit strip, 12 inch, and divide by the spacing, okay, because I have another strip here, I might have a spacing here because this may not be 1 bar per unit foot, okay, may not be 1 bar per unit foot, all right, so I want this that is equal to AS per foot provided, okay. If you forgot where this come from, you can look back in the beginning of the lecture notes, okay? So this has to be greater than or equal to 0.343 inch square per foot. All right, it's not AB, but conversion AB multiplied by 12 divided by spacing has to be bigger than that. Now with this, we can select the bars. So now I would say select the bars, right? Now we already selected the bar, isn't it? We say select number 4, okay? Okay, we already have that. We just don't know the spacing. We just don't know the spacing, isn't it? So spacing should be smaller or equal to AB multiplied by 12 divided by AS per foot. Okay, so this is AB, which AB for number 4 is 0.2 inch squared for number 4, okay? So this is 0.2 inch squared multiplied by 12 and divided by, this is 12 basically inches, divided by AS per foot. This number is right here, so 0.343 inch squared per foot, inch squared per foot, okay? Inch squared per foot. So now I got, this is per foot, isn't it? This is per foot, so I got to convert that into inches, right? So 0.343 inch squared per foot means that per 12 inches, right? 12 inches. So I got this number to be about 7.06 inch, okay? 7.06 inch. All right, okay. So that is the spacing I need to have. That is the spacing I need to have. So now with this one, I say S has to be smaller than 7 inches. So select S equal to 6 inch. Okay, I want to be denser than that. I want to be denser than that. All right. So given this as AS per foot provided, okay, now equal to AB multiplied 12 divided by 6, which is the spacing, right? So that gives me 0.2, 12 divided by 6. So I have a 0.4 inch square per foot, and that is provided. Okay, so at this point, since this is provided, I say AS per foot provided, okay, equal to 0.4 inch squared per foot. That is greater than the AS foot required, which is 0.343 inch square per foot, right? So that means I satisfy my requirements, I'm okay, right? So this is okay, all right? But in terms of flexure, it's a lengthy process. It's a lengthy process. We again have to confirm, that it's yielding and it is tension controlled because we assumed that phi equal to zero point 0.9, right? So we again have to find A, which equal to ASFY, and divided by 0.85 F prime CB, okay? And the top here, this is now 0.4, okay? This is 0.4, and that is what you provided here, okay? Inch square per foot multiply the yield strength, which is 40 KSI, and divided by 0.85 multiplied by 4 KSI multiplied by 12 inch. Okay, so now my A should equal to a 0.392 inch. All right, so this is my newly finalized effective compressive zone. And to get my steel, right, the strain of the steel, I need to do C, remember A divided by beta 1, okay? And beta 1 in this case equal to a 0.85 since it's 4 KSI concrete, so this equal to 0.46 inch for the compressive zone C. All right, so the last, again, assume one layer, right? Because assume we only have one bar here, assume one layer. So epsilon T, remember in tensile, should equal to epsilon S, right? So that equal to D depth minus C divided by C and multiplied by epsilon Cu. So bring the number in, D equal to 4 inch, C equal to 0.46 divided by 0.46, and then multiplied by 0.003. So I have the final number to be epsilon T equal to 0.03. Okay, and this number indeed is greater than 0.005. So not only yielded, but also tension controlled, right? So phi equal to 0.9 confirmed. All right, see, phi equal to 0.9 confirmed. Now, finally, right? Finally, remember the process. My nominal flexure strength Mn would equal to AS Fy and multiplied by distance minus half A. All right, and you plug the number in. I'm just going to save this step. Is equal to 5.1 kip foot per foot. I cannot emphasize this enough. The unit kip foot per foot. All right. Say a wise man says in exam number 2, I make a problem asking you what is the moment resistance for this one-way slab, and you give me some number and you use unit kip foot per foot. If I don't see kip foot per foot, which means if I don't see the per foot unit strip division, I will have to deduct 50% points from that problem. All right. So I hope I made that clear. Okay. So make sure you understand the unit, right? Why there's a per foot and always carry that throughout the calculations. All right. So with that, I have my design VMM design capacity, which is 0.9 multiplied by 5.1 kip foot per foot, So that gives us a 4.56 kip foot per foot. And if you really want to compare, this number is indeed greater than the applied factor moment equal to a 3.94 kip foot per foot. Okay, kip foot per foot. So this means we're okay. This means we're okay. All right. All right. So with this now, we can say, look, I have my reinforcement detailed, right? So looking back, I just want to draw the section to tell everybody this is my design. Hey, so this is per unit strip, and forgive my poor writing here. So 12-inch, and I have a bar right here, and the depth of it equal to 4 inches. The height of it equal to a 5-inch, and I have a bar, which is number 4. So that is my section per unit strip. So I'm pretty stoked about it. I have my final section design. I'm happy on all that, but don't forget, right? Don't forget, per the flexure reinforcement design criterion, right? We also have to check to see if the AS min is satisfied. The minimum reinforcement area, right? The minimum area reinforcement is exceeded, right? So what is this? AS min by the code equal to a 0.002 two-thousandths of BHF. So 0.002 multiplied by B, which is 12-inch, F is 5-inch. So I got this number to be AS min equal to a 0.12-inch squared. But again, don't forget, this is per foot. I always say, right, this is per foot. Don't forget about that. So that is the minimum area reinforcement required for the slab. And what we have provided for is 0.4 inch squared per foot. It's greater than the minimum requirement, which is 0.12 inch square per foot, right? So at this stage, we're okay. At this stage, we're okay. All right. So does that mean we're done? Does that mean we're done? Not quite. Not quite. Right. And why we're not done yet? Because we need to check the two sub criterions. Okay. Two sub criterions. What are those two sub criterions, right? So S max has to be what? Has to be smaller, right, than, okay, the following, right, smaller than 3HF or 18 inches. So this is 15 inches because HF is 5, remember? And then I have this to be deflection controlled, remember? Deflection controlled. And I also need to verify if this is smaller than 15 multiplied by a 40,000 divided by Fs minus 2.5 cc. So write this number in, 15 multiplied by 40,000. Now what is Fs? 2/3 of the yield strength, which is 40 ksi, okay? And then minus a 2.5 multiplied by cc. What is the concrete clear cover? 0.75 inches, okay? So I got this number to be a 20.6 inch, right? I have one more, which is 12 and multiplied by a 40,000 divided by a Fs. So I got this to be 18 inches. Now, if you remember, these are the crack control. These are the crack control sub criteria. All right, so let's go over it, right, to see which number of controls I have. 15, right? I have 18, I have 18, I have 20.6, I have 18 here, right? These are all the criteria, right? So what are the max? So all these 15 is the smallest number, governs, right? So this governs, and I need to check as provided from our previous calculations, 6 inch. That is much smaller than the maximum spacing requirement is 15 inch, right? So we're okay. We're okay. All right. Now, finally, we're fine, right? Finally, what it is that we're saying is for a one-way slab, right? One-way slab, we're gonna have a number 4 bars, and this is 6 inches. So number 4 at 6 inches of one-way slab, and the depth of that is d equal to 4, and the height of that is 5 inch. Okay, so this is the first problem, right? If you go all the way back, this is only answering the part 1, which is a flexure, okay? Sorry, this is, let me just use the category 1, flexure design, okay? Flexure reinforcement, not this one, okay? Forget about that, okay? Flexure reinforcement, this is only for flexure. So we basically just finished laying down the bars in this direction, okay? Just finish laying bars in this direction, okay? And that is the main direction. Now we're going to look at shrinkage and temperature, which is laying bar in this direction. So this is shrinkage and temperature. Okay, shrinkage and temperature. So let's continue, right? Now we have laid the bars in the flexure. What about shrinkage and temperature? So 2, shrinkage and temperature reinforcement. Shrinkage plus temperature reinforcement. Okay, so how to determine that? So first of all, we have to look at AS min again. Remember from shrinkage and temperature, right? So AS min has to equal to 0.002 BHF, right? So this equation is identical to the previous equation, right? So we can carry this to be 0.012 inch squared per foot. Okay, and now with this I say, looks like I just need to provide reinforcement that exceed this number, right? But what about spacing? Right? So what we can do is, let's assume number 4 bars. So the whole idea becomes that I have to provide AB, which is number 4 bar here, multiplied by 12 divided by spacing, has to be greater or equal to AS min, which is 0.012 inch square per foot. Okay, so that's all I need. But, okay, but I have to take a look at the spacing requirement. All right, so for shrinkage and temperature, okay, right, the sub criterion, this is new, okay, fellows, this is new, on crack control is valid. Okay, is on crack control is valid. So S max should be less than 2 equations. What are these two? Here and here. Only these two, okay? Deflection, not so much issue. Correct? Yes. So what are these two? 15. This one, so this is 20. So let me just write it out. So 15, 40,000 divided by Fs minus 2.5 cc. Since we calculated this one already, and this is to be 20.6 inch. Let me get this number. Yes. So the other is, the other is 12, 40,000 divided by Fs. That equal to 18 inch. So I have to be smaller than both of them. So this one governs. Okay. So if this is all we need, then I would say, look, we already assume number 4 bars, right? And this is the spacing requirement. So I can say select number 4 bars at a spacing of 18 inch. for shrinkage and temperature, for shrinkage and temperature. Okay, so just to remind you that this is for a one-way slab. Again, this is for one-way slab. All right, one-way slab. Support, support, okay? And we just provided the flexure reinforcement in L1 direction, right? So the red one is flexure, remember? The red one is flexure. So we said this is spacing or reinforcement number 4 at 6-inch. For shrinkage and temperature, now fellows, they are in the L2 direction. Okay, they're in the L2 direction. And the spacing between them are number 4 bars at, this is 18-inch, quite wide of distance, quite large of distance. All right, so now this is our design. Number 4 bar at 6-inch in the L1 direction, and number 4 bars at 18-inch in the L2 direction. And that is my design for one-way slab. Okay. All right. So let me pause for a second. And any questions on this one-way slab design? Any question for it? Okay. All quiet. I think it's maybe the spring break effect. Takes a little bit of time to digest. So go back, review this part, and really understand how to do this. Okay. Really understand how to do this. This will show up in exam number 2.
Hey, exam,
Question?
do you want a diagram like that?
I'm sorry again. You say draw the diagram like this.
Yeah, do you want it drawn like that?
In homework, yes, but in exam, no, not necessary.
Okay.
Yeah, as long as you understand, which one you're putting down. Because uh, I'll be perfectly honest with you guys. In the exam number 2, most likely I'm not going to ask you to work out full solution on the one-way slab design, but instead I might ask you guys to do a fill blank, right? So for example, I may say, what is the design for? Just saying, okay, design for flexure, right? And I give you a fill blank, right? So I need you to write like number 4 at 6 inches. What is for temperature and shrinkage, you know? So I would expect you write number 4 at 18 and justify the process, and that's it. All right. Okay. All right. So pretty straightforward for one-way slab. All right. But do go over them. Be careful on the unit. All right. Any other question before we move forward? Before we move on? Okay. All right. So that concludes the one-way slab problems. All right. Now we're gonna get into the lecture 17 today, but just get it started. We'll not be able to finish that today, but I just want you to have a peek at it. Okay. So we have done with one-way slab, matter of fact, right? And we're happy with it, right? So let me go into lecture 17 and open up a new conversation, right? This is still on one-way slab, all right? Still on one-way slab, but instead of simply supported, we're gonna talk about continuous support, all right? Now let me say, what is the difference, Bob? I mean, we went over such a in depth about the simply supported condition. What about this continuous one-way slab story? All right. So remember last time we showed you the drawing, right? So every time we talk about the simply supported condition, we always draw this nice slab-ish drawings like this. Okay. And then we show that there's a support somehow like this support, right? And we show that, look, 2 types of reinforcement. I always use red for the main flexure reinforcement in the short span direction, which is the L1, remember, for bending. And we have just talked about it, and temperature. So let me just draw very sparsely temperature for the other one, right? So this is Fletcher. Okay. So for the moment diagram, right? For the moment diagram, simply, oh, let me use different color. Apologize. Simply just draw the uniformly distributed load like so. And for the moment diagram, it's even easier, right? So it just have a maximum moment somewhere in the middle and is positive, right? So go this way. So this is omega, this is omega u, this is omega u L1 squared divided by 8, and this is L1, right? This is L1. And this is simply supported one-way slab, right, on the left-hand side, right? Straightforward, right? Nothing difficult, nothing difficult. And the reason is that it's simply supported. The reason that is simply supported. So if we switch different scenarios, say, most of the cases actually, it's not that simple. It's not that simple. Matter of fact, it's more complicated than this. And we have drawn similar diagram before. We have drawn a similar diagram before, and it looks just like this, right? So I have an integrated spandrel beam at the end, and I-beam, sorry, underneath it, beam underneath it, beam underneath it, and then L shape again like that, and then this is the slab, right? So now if I draw the side view like I did here, so I have to say, this is support, and draw a straight line, and apply loading here. But before I do that, I have additional support, additional support, additional support. Okay, so I may have a problem is that when I put my load on it, I may have this type of loading. I may have this type of loading, right? Or I may have evenly distributed loading everywhere. Okay. Okay. And you say, Bob, what's the difference, right? I'm just going to put all my load on it. Wrong, right? That's not going to work. Why is that? Is they don't necessarily give you, or they don't necessarily produce the maximum moment, maximum bending moment at each section, all right? So if you take a look at fully loaded span, every span was loaded, equally loaded, and you say, let me just apply the maximum distributed load on it. Now, the moment here at the negative junction, right, is going to be maximized, but the moment in the middle span may not be. The moment in the middle span may not be. So it not necessarily give you the maximum scenario where you cannot take it to design, isn't it? So we have to usually use the influence line method to determine what is the maximum loading on the section. What is the maximum loading on the section? So for this, we call it that ACI actually says when design, we need to use patterned loading. Okay, define pattern loading, right? What is pattern loading? All right, so this is the first thing I want to explain to you, okay? So by ACI, patterned loading refer to the loading that will produce the maximum moment, okay? Or produce the maximum moment. All right, and of course, right, this maximum design moment shear is in the different locations, right? So ACI says, the code says, and this is 318 on 8, section 8, 11, 2, it says that they will, well, they already, but they define loading patterns. They told us, right? They already informed us what kind of pattern we have to use to determine the maximum design moment. And shear in continuous, okay? Not simply supported. You don't need any pattern for simply supported case, right? For continuous beams and one-way slab. My short way of writing one-way slab, okay? Okay. So this has been determined already. Okay, has been determined already. So you say, okay, it has been determined. So what does it look like, right? It tells you that following pattern has to be followed. First of all, is that you need to put the factored dead load on all spans, okay? But plus factor live load on two adjacent spans, and that's it. So this is scenario number one. Essentially, you have to apply this to check for your design moment. So what does it look like? Look like this. So if I'm gonna make an example for a 4-span conditions. Okay, 4-span condition. So I have end support. I have another one here, another one here, another one here. So this gives me 4 spans. So I call it A, support B, C, D, E, etc. Right? So let me just put the support underneath it so you know there are supports. So all dead load on all spans factored, right? So first of all, let me put all spans under a 1.2 dead load. 1.2 dead load. Okay, so this is distributed dead load. Right, so this is 1.2 omega dead load. Okay, now it says on 2 adjacent spans and no others, right? So right, let me use different color so you can see it. So for example, section B here, right? I'm trying to find the maximum bending moment at this one for design bending moment at this one. So what I will do is I will provide live load 1.6 live load on the adjacent span. Okay, so this is 1.6 live load on the adjacent span. That will produce the maximum bending moment. Matter of fact, it's going to be something like this, right? Maximum bending moment at B here. Okay, so this is scenario number one. Essentially, ACI says apply this and find out the moment at each junction, A, B, C, D at the support, and also at the middle span, All right, and compare this, right? Compare this with scenario number two. That is factored dead load on all spans, plus factored live load on alternate spans. Means, okay, you try scenario number one and get the moment, right? And then let me draw it again, although it's a bit time consuming, but same structure, all right, and same support, A, B, C, D, E. And not only we need to provide the O dead load on the span, 1.2 dead, that is 1.2 omega dead load, but also on alternate, right? That means if I want to put it here, 1.6, that is live load. So I need to put it here, 1.6 live load. And that is alternate span. All right. So essentially is for B, right? Just I'm taking the example here. Okay, this is EG, right? For example, for B, then this moment right here is a little bit less, right? But at the middle span, it will be a little bit higher. So something like this. Okay, so here will be something like this as here as well. Okay. Right, so that will be my moment diagram. So I just need to compare my moment diagram from pattern 1 and my moment diagram from pattern 2 and find out the maximum moment at each junction. at each junction. And that will give me the maximum moment at A, B, C, D, E, and also midspan. And also midspan. So that, ladies and gentlemen, is the concept. Okay, is the concept. All right, I'm gonna stop right here and we'll resume by showing one example on Monday. Okay, one example on Monday. And unfortunately, this will be covered by the exam, but very small portion of it. So Monday will show you an example, and I'll leave the homework right now, but it's not due in spring break. It will be due afterwards, the Thursday after spring break. Okay, and we'll go through one example on Monday and then go into the review on Monday as well. Okay, so I'm gonna stop right here. Feel free to stay behind, ask me any questions, or else have a nice break and see you after the break. All right? Okay, bye now. Thanks.
Professor,
Yep.
I hadn't seen the notes from last lecture yesterday on Canvas.
You should see it because it's the same lecture number 16. So I just replaced that with a new version.
Oh, okay.
Yeah, can you go back and check? If it's not, just let me know. Okay.